Hello everyone, my name is David Hendricks, and this is my colleague Andrea Barberio, and we are here from Facebook, and we are going to talk about how we are turning our Linux engineers into firmware engineers. So I'm going to go over a little bit of basic information about firmware, what it is, and the problems that we're facing and trying to solve. Some of this might be repeated information for some of you. I assume, how many of you have worked with system firmware or BIOS in some form or another? Okay, so yeah, about 2/3 of the room is pretty well acquainted with these concepts. So I'll just make sure we're all on the same page here. So firmware is a bit of an overused term. This talk is going to focus primarily on the system firmware. So the system firmware, as we're defining it, is the firmware that runs on the CPUs, and we call it the system firmware because it tends to be the catalyst that initializes a lot of other stuff in the system. So it's the first bit of code that runs when the CPU is turned on, and sometimes it's referred to as the BIOS, especially in the x86 world, though that term is outdated, as we'll discuss a little bit later on. For our purposes, it serves two fundamental purposes. It serves two fundamental functions. The first is to initialize your hardware after reset and load your operating system. Those are the two main things. There's some other stuff as well, which Sarathi and Gundrala covered, such as RAS features and some runtime services, but we're not going to get into those for this talk. So firmware is an important part of any computing system. It's very integral. You know, anything with a complex SoC needs something to bring the processor into a sane state so that it can actually run the application that it's intended to run. Code running this early generally has to deal with certain constraints that, if you're coming in from an applications development perspective, might seem a little bit bizarre. For example, you probably don't have DRAM. no memory, no caches, just these simple things that nobody really thinks about, you suddenly have to think about when you're dealing with system firmware. And of course, on x86, things get even more bizarre, since even your modern 30-core Xeon processor running at several gigahertz comes up thinking that it's a 40-year-old 8086 in 16-bit real mode with 1 megabyte of address space. So there's quite a bit of work that needs to be done to actually bring your processor to a state where it can run what we would think of as normal code. And then once you have the processor in that state, you have to go through the effort of initializing a lot of devices and loading your operating system target and then executing that. Simple, right? So, of course, it's not that simple, otherwise we wouldn't be here. So I'll just go through a couple of examples of how this problem has gotten more complex over the years. An obvious example is local booting, the simple act of reading an OS target from your local storage, perhaps a hard drive. Let's just call it that for simplicity. So first off, the sheer quantity of devices has obviously exploded. Back when BIOSes were first being developed, you may have only had to worry about one or two possible interfaces that existed at the time. Nowadays, we have many generations of many devices with different interfaces, protocols, host controllers, and the combinations are just exploding. Here are just a few examples. You got SATA interfaces, you got NVMEs on PCI Express. You might have eMMC especially if you're working in the embedded space. And of course, we have removable media these days, which wasn't really a problem 30 years ago. So you have to worry about hot pluggable things like MMC cards, USB drives, and each of those has many different generations and standards. Anyone who's dealt with USB knows this pretty well. USB UHCI, OHCI, EHCI, XHCI, and all the fun with Type-C. Oh man, that's a lot of fun.
You missed the floppy drive.
Oh, the floppy drive, of course.
Removable media #1.
And of course, things have gotten a lot faster over the years. Before you had some simple low-speed links that you may have had to worry about. These days you have high-speed links that you may need to do some pretty complex configuration of the platform itself, very board-specific things like configuring power and clock trees, you probably need to enumerate and configure buses first before you can even talk to your device. You probably need to probe some capabilities and set some things up on your host side as well. And you also have to set aside some memory regions for MMIO. So there's quite a bit of work that needs to be done just to get to the point where you can talk to your device, whereas it used to just kind of be like, in-bees and out-bees. And then finally, okay, so now you can talk to your storage device, but now you have to actually load and execute your operating system target. Way back in the day, the way to do that was to simply read the first thing that you could find on the disk, cylinder head sector 001, load it into memory, and then blindly execute it. These days, you might actually want to probe a few different media devices, figure out which one you want to boot based on some kind of policy. Maybe you want to prioritize removable media. Maybe you want to completely ignore removable media because that could be an attack vector. Might want to encrypt what's on the storage device. So maybe you don't just want to blindly execute it, but you want something that you verify. Maybe you have to read an encrypted file system, and then maybe you have to mount that file system. So you might need file system drivers and all kinds of stuff that needs a lot more code and a lot more libraries. So that's just an example of how local booting has gotten a lot more complex. So network booting has also gotten a lot more complex. That's the other major way we boot in our data centers is we download a OS target and then we want to execute it. And of course, networks used to be a lot simpler too. Back in the day, network booting used to mean you would load your OS image from a machine maybe across the room or maybe a few racks over, probably on a local area network or at least some kind of network that you controlled and you trusted. These days, we want to think of our networks on a global scale. And we like to be able to netboot an OS image from maybe another data center or around the world somewhere, or maybe out in the field over an untrusted network. So like storage, there are many interfaces and many protocols with varying levels of complexity, robustness, and security. You might want to netboot using a simple Ethernet interface, or some of the OCP systems that you see downstairs have those fancy shared Mellanox interconnects. And in some cases, you might even want to boot off something like Wi-Fi or a cellular network. The current network booting technology was mostly designed decades ago. I think TFTP came about in the 80s, Pixie came about in the 90s, and it's persisted quite a lot, and there have been some efforts to improve it. But a lot of the industry still boots using these really antiquated protocols. You wouldn't send your credit card information or any personal data about yourself over the open internet using TFTP. But why would you boot your data center that way? Right? So definitely look up Chris Koch from Google. He has a great talk called Network Booting in the 21st Century. So we're trying to kind of push these mechanisms forward. So that's just a couple examples of how things have gotten a lot more complicated over the years. And so why does Facebook care? Well, here it is in a nutshell. We have a lot of data centers and a lot of computers. We have a huge infrastructure now, and we have many generations of configurations and platforms that we have to support. So obviously, that was a lot of networking gear and servers I just showed you. It's come a long way since the days when Facebook ran on a computer in Mark Zuckerberg's dorm room. Now we have many, many, many dorm rooms worth of servers. But that's not all. We're not just concerned about the data center anymore. And pictured here is some open cellular hardware, which currently runs on open source firmware using the same code base that we're actually using for our data center hardware. So Open Cellular is an effort to bring inexpensive cellular access to developing parts of the world that are currently unserved. It's one of the many projects that fall under the Telecom Infrastructure Project, which is sort of a sister project to OCP that is focused on connectivity initiatives. OCP has over 100 members, TIP has over 500. So these are big, big efforts with many parties involved. We're involved with a full range of hardware projects, from embedded to networking to servers. And this means we must also support firmware across a broad range of products. Each of these things has system firmware. How do we deal with it all? So many platforms, many firmwares, many bugs, and many headaches. And of course, it's only getting more complicated as we're growing. Traditionally, there would be a unique firmware for each individual platform. Even if they were, UEFI firmware, that UEFI firmware may have come from different vendors using different versions of EDK2 code, and oftentimes with different tools to support them. So even though they had kind of the same DNA, they still had to be treated as separate firmwares. Firmware has not received as much attention as hardware and software. And as our hardware portfolio grows, this has to change. The OCP Open System Firmware effort aims to address this shortcoming. Firmware is an important part of every product. We work with many partners, and for our own sanity, we have to act as sort of a point of coherency to ensure that we can properly support all the projects that we're actively engaged with. And being open helps us to accomplish this. Those of you who have worked in the firmware industry for many years know that the old way is to sign a whole stack of NDAs, maybe some contradict others, who knows, set up access accounts, keep track of who's allowed to look at what, and so on. You'd have to curate email lists and move code in between different forks of a code base, which is painful and error prone. Party A might have access to this part of the code base, party B might have access to this part of the code base. There's a bug that's found, and it goes into this code base, but not this code base, and it's just a mess. And it's just slow as molasses compared to what people are used to today. We want partners to be able to pull down, share, contribute code out in the open with none of these headaches. We want to cut the bureaucracy and the red tape and maximize the engineering productivity and move faster. So there are many parts of this puzzle, many pieces to this puzzle, and each of them is a lot more complicated than it used to be, and these problems are growing in size. So let's briefly discuss one of the ways in which the industry is attempting to solve this. So I pick on UEFI because I figure pretty much everyone here is familiar with UEFI, but a lot of the same concepts apply to other firmwares as well. So system firmware was once a monolithic blob called BIOS, but not anymore. These days it's more like a distribution, and it's divided into several components, which we'll walk through. So the first component that runs on the CPU predominantly is the PEI phase, and that's the part that initializes the core silicon. That's the thing that turns on CPU features like your caches. It'll initialize DRAM and actually get the processor to a pretty reasonable state. The next few steps in this particular flow, that's where things get pretty interesting. So there's the Dixie phase, which is driver execution environment, and that sets up hardware interfaces, which are used by the later phases, BDS and TSL. So BDS is the boot device selection phase, and TSL is the transient system load phase. The TSL is things like grub, for example. So BDS and TSL are where applications get invoked to decide things like where to boot from, and may include things like graphics drivers, especially if you have one of those cool gamer motherboards where you go into the BIOS setup screen and it renders spinning fans and temperature, mercury thermometers and things like that. A network stack, because sometimes you have to network boot, crypto libraries, and so on. And then after all that, you finally reach your runtime, which in our case is usually Linux, because Facebook uses Linux a lot. So the result is that booting has gotten very complicated, and to deal with this, system firmware has become basically an OS in its own right, with drivers, a network stack, crypto libraries, graphics, apps, a shell, etc. So a lot of people don't really think about it, but all these things combine into millions of lines of code that run at the highest privilege level, set security policy, and have unfettered access to all your networking and storage resources. And yet somehow this has been overlooked, and the ecosystem has remained stubbornly closed throughout the years. The tooling needed to support this has also remained proprietary and specific to a limited range of products. Just as an extreme example, the firmware update utility that you run to update your server would probably brick your laptop if you ran it on your laptop. Or even very similar platforms like maybe Tioga Pass and Project Olympus probably have completely different firmware update tools, even though it's very similar hardware. So what we want is something more open. If we're going to have an OS in the system firmware distribution anyway, it should be something familiar that we have experience working with. And so in this case, I put the LinuxBoot logo up there because we don't yet have a cool logo for open systems firmware, but maybe we will at the next summit. So a lot of these concepts apply to open system firmware in general. But anyway, so we want something that's open that we're familiar with. For us, Linux is very familiar. We have teams of engineers who are currently supporting Linux at all levels: kernel, tools, services, etc. Our engineers are very experienced with this code base. So things like auditability and debuggability, both for just debugging and also for security. It doesn't just mean that we get millions of lines of code and we have to comb through it and it's like, three-person's job to sit there for a year and stare at that code base. These are people who use Linux every day to accomplish things in their normal day-to-day work. So it's auditable in the sense that our engineers aren't just staring at some third-party code drop, they're actually working with it and developing it on a day-to-day basis. And the same goes for debugging. It's not just that we have tools available. We have people that use these tools and develop them in their day-to-day work. So for us, Linux is where the development momentum is. So that's how we're turning our Linux engineers into firmware engineers. And finally, rather than being product-specific, Linux is very portable and reusable. I mean, you can run it on anything from a server to a toaster. So that broad range of products that I described, they all run Linux, and therefore, that's a great opportunity for us to exploit Linux in our boot path. So more generally, in open system firmware, so we're pursuing the LinuxBoot approach. And there are two current work streams in the open system firmware project that kind of reflect some of the ideals that I just laid out. The idea that we want something open and something that's familiar to our engineers. So OpenEDK is something Gonzalo talked about, and that's a fully buildable UEFI implementation. And for them, of course, Microsoft has decades of leadership and expertise in UEFI, so for them it makes perfect sense. For us, we have a lot of, well, Facebook's not decades old, but we do have a lot of experience with Linux, so in our case, Linux works pretty well for us, and that's the same story with Google. So there are these two different work streams. They are divergent in some ways, because we're just using what we know in our boot path, but there is still a lot of opportunity for collaboration, and that's why we're here. They both have same or similar hardware initialization portions. The difference is that second part where you load the operating system. And which should you use? Well, it depends on your use case. Both aim to offer fully buildable, customizable boot solutions that will fit into your infrastructure. You don't have to change your infrastructure for the firmware. You should change the firmware for the infrastructure. And there's plenty of opportunities to share code between the two, especially for things like the runtime services, RAS features, and so on. So going on a little bit more about the Linux approach, LinuxBoot approach, and why we're interested in it. So the main idea with that is to put a Linux kernel and an init ramfs in the boot ROM alongside the part that initializes the silicon. So you do your bare minimum silicon initialization, and then you jump straight to a Linux kernel. Since the Linux kernel in this case lives in the boot ROM, the part that initializes the silicon only needs to know how to read the boot ROM. It does not need to know how to access your network. It does not need to know how to read your file systems or anything like that. We want Linux to handle that part. So we do the minimal silicon initialization and then jump to Linux as soon as possible using Linux to boot Linux. This gives us the production quality drivers and networking features that we utilize at runtime. Obviously, if a lot of our infrastructure runs on Linux, these drivers have to work. Therefore, they have to work well, and a lot of the problems that we've seen in the boot process where some old forked driver from maybe an antiquated version of EDK makes it into the firmware code base and fails to get an IP address because it hit a corner case in the DHCP implementation or something like that, that goes away. And of course, this enables us to add features and tools as needed. It allows us to reuse libraries from our runtime, and we're able to develop, debug, build, and deploy on our schedule. In other words, this enables us to move fast. And a few other side benefits. Things like the security model can be tailored to the threat model and use case. For example, a server in a data center has different physical access and serviceability requirements than an open cellular platform that's 2 days away from the nearest town out in rural Africa. So it's really helpful for us to be able to identify exactly how we want to service these things, how we want to maintain these things, and then really customize the firmware to maximize our ability to service them remotely or even locally. Like in the data center case, you want to be able to have a very specific recommendation go to a data center technician who's sitting 5 minutes away. We can boot really fast. Gundrala had or maybe Sarathi had, they mentioned they have a nice quick boot demo at the Azure booth, so definitely check that out. It's very impressive. We have a quick boot demo as well. Booting fast, it's not just the fact that you're booting fast, but to enable booting fast, you can also strip out a lot of stuff that you don't need. And this goes back to eliminating sources of bugs and potential security problems. We're able to modernize our code development process. We want publicly visible code reviews. We want public discussions. We want people to call into the OCP, Open System Firmware meetings. And we want these to be out in the open so they can be reused and referenced. And also, we want a full history of the code. We don't just want a couple millions of lines of code sent to us via a zip file in an email or something like that. We want something where we have a full Git history and can trace the origin of any line of code. This is especially important in this day and age with very sophisticated attackers who may have influence or may be able to break into a partner's infrastructure. We want to be able to audit every single line of code that we run. So in short, we're trying to turn this into this. And I'm going to hand off to Andrea, who will tell you about that handoff in between the Linux's bootloader or LinuxBoot part to the runtime.
Thank you, David. All right, my name is Andrea. I am not a firmware engineer. I am not a hardware engineer. So what the hell am I doing here? I'm a production engineer, which is, for Facebook, is the organization that takes care of the scalability, reliability, security, and speed of the infrastructure. I work in a team that is called OS Provisioning, and the second part of the presentation is going to focus more on the problems that we face at scale with firmwares in our infrastructure. So my team basically automates the installation and reinstallation, basically the whole life cycle of operating systems on Facebook's infrastructure. It sounds like a simple thing. It is actually pretty easy on a single machine. But when dealing with large scale, of course, things get more complicated. There are a lot of moving parts. There are a lot of services that are involved. Network installation, of course, involves the network, which means that there can be additional noise due to unexpected failures or rerouting events, any noise that the network itself can introduce. So to give you a better sense of how this works, how does this look from our perspective, let's look at the host perspective. How does a reinstallation in our infrastructure looks like? These are the simple steps. The machine powers on, either from a cold boot or from a reboot. Then it tries to acquire the network configuration via DHCP v6. This network, all of this happens in the firmware, of course. Once the network configuration is acquired, our servers will have are configured to say, yes, if you are supposed to reinstall yourself, you have to netboot, you have to download this network boot program. And how do we download the network boot program? TFTP, which is pretty old. It's we were born in the same year. Once the network boot program is downloaded, it is executed by the firmware. We don't care about what happens next. Let's focus in uniquely on the host side and what happens in this process. So what's wrong with it? Well, some DHCP and TFTP implementations are buggy. TFTP is a pretty old protocol. It's pretty slow. It's quite unreliable. It definitely does not work on long distance because of strict timeouts. Not timeouts, but basically it doesn't have windowing, like, for example, TCP. And different machines may also have different firmwares, which means we have also different sets of bugs. One vendor firmware may have a bunch of bugs. Another vendor firmware may have completely different bugs. So we have to find and chase and fix and roll out updates for all of them. This is not exactly sustainable. Say that, okay, but how unreliable this is? Not really much. How to put it? So it doesn't fail that often, but at a large scale, it can translate into a large number of broken machines, which means a lot of operations, sometimes manual operations for our team. So anything that cannot be automatically remediated, of course, has to be addressed manually. And this is definitely not something we enjoy to do. So what we need to get past of these problems. First of all, we need reliable clients. As I said, DHCP and TFTP may be buggy. Even if less than 1% of the machines are buggy, it's still a lot for us. But we also need better protocols. TFTP, as I said, it's slow, it's unencrypted. It's all the bad things that you can think of a network protocol in 2018. And why not using HTTP or even better, HTTPS? We get the benefit of being able to download large files in short amount of time, encrypted, long distance, and anything. We don't need any more to boot from geographically, latency-wise, nearby machine. But above all, we want to control the implementation. We want to know what we are running, since as a company, we have a lot of data on our machines. We also want to be completely sure that we know what it's running on our machines, that we have control over them, that we can find the bugs ourselves, we can fix those bugs, and we can roll out the fixes as soon as possible. So say that LinuxBoot can, we believe that LinuxBoot can really simplify provisioning. We can use tested DHCP and TFTP, or even better HTTP implementations, which are potentially the same ones that we run in production machines. For example, you could use wget or curl or anything that you really want to use. Another big benefit is that we can run consistent versions of firmware across the fleet. We don't depend anymore on multiple vendors with different code bases and different versions of firmwares, but we can have one single code base that runs everywhere. So once you learn how to upgrade the firmware on one machine, the same tools can be reused for the same machine, and so on. You can do troubleshooting with the same tools, and you don't need to, you're not tied to a specific vendor and version that you have to remember on the runbook and see, oh, how do I troubleshoot this on this monolith or this wedge or whatever it is. But as I said, the really big thing for us is that we know and control what's running on our machines. All of that above for us means that we expect to largely reduce the net booting failures, which from my team's perspective means reducing a lot of operations. Reliability is not the only issue. We also have firmware upgrades because, of course, the fleet has to be maintained as up to date as possible. So at the moment, updating a firmware means that we depend on different vendors. And different vendors may have different standards in code quality, in responsiveness, basically how much time does it take from finding the bug to getting the bug fixed on their side. But it's not just that. So vendors may not be able to reproduce the bugs in their infrastructure. We have a quite complex infra, which may be different from many other infrastructures. They may have a smaller one with different setups, and they may not be able to reproduce the same bugs that we can see. Which may further slow down the process on their side of fixing the bugs. Putting all these things together, let's assume that at this point the vendor has fixed the firmware. They hand off to us a new binary blob, and we need to run our own validation. So they have to do their testing. Let's go back. We have to detect the bug first, contact the vendor, get them to test it, to validate the bug, fix the bug, give us back the fixed images. Then we have to run our own validation, which means it's a second additional step that further slows down everything, and communicating with external companies is, of course, slower than doing everything internally. Basically, this means that the time from detecting a bug to getting it rolled out to the whole fleet can take months or even longer, and this is just not acceptable. We want to speed up the process, and we want to be able to do debugging on our own. So another point that I mentioned is testing of the firmware. The testing is mostly split in two parts. One is done by the vendor, one is done by us. Whatever the vendor does, it may be the best type of test in the world, but we have no idea what they're doing. Even if they try to give us a better insight, we really don't know exactly what's going on, how it has been tested, what were the responses, the regressions, and so on. So once they hand off the blob, we have to treat it as a black box. We have to treat it as tested, but still it need to be validated by us. And of course, we have our own testing infrastructure, our own test cases, which may be sometimes better, sometimes worse than what the vendor has done, sometimes overlapping, or basically we don't know what they covered and what we did cover. We may have gaps in what has been tested. All of these things together, again, lead to slowness in the deployment to production. And imagine this, it's fixed, but then we realize that either the bug is not really fixed because there is another edge case, or we find an additional one. We have to start all this process over again. Multiply this by multiple vendors, and it's definitely not something we can happily sustain. LinuxBoot, we think that LinuxBoot can help speed up a lot and minimize all the steps, which basically means reducing as much as possible the time frame where a firmware image flashed on a machine is buggy or has a security flaw. We're talking about open source firmware, which means that we get automatically all the benefits of open source. Most of them are obvious. I'll just go through them anyway. I want to make this explicit that this is really good. Auditability is a big thing for us. We can see the code. We can understand what's running on this machine. We can understand if they are doing the right thing. If they're not doing the right thing, we know how. But since we can also modify the code, we can actually fix it on ourselves. Debuggability is another big thing. As I said, my team automates the installation, which also means operations. Debugging something that is not working is very important. How do you do that with closed source firmwares? Well, you try to boot, you see if it works, you try to understand the signals on the other side. For example, did you get the DHCP packet on your server side? Yes or no? Well, okay, whose fault if it doesn't get there? It's the switch in between, all the routers in between, some cable issue, some network flapping, or it's the firmware itself. With closed source firmwares, we just have no idea. With open source firmware, of course, we do. We can even run common troubleshooting tools like, imagine running TCP dump on your firmware. Sounds interesting, right? Transparency is also really important because Linux is open source and the other software we use, like Core Boot and Root, are all open source. So we understand the security model. Again, it doesn't mean that it's a better security model, but at least we have an insight into it and we know how it works. We can work around its shortcomings and we can benefit from its strengths. And it's obviously good. But portability is another big thing. As David mentioned, we don't run uniquely on x86. We also have embedded platforms like OpenCellular that has multiple architectures like ARM64. And Linux can run on so many architectures. The toaster example was really good. And not only Linux can run on many architectures, but also the user space RAMFS that we use is written in Go and can easily be cross-compiled for multiple architectures and built in seconds. Another benefit that I really appreciate of this kind of change is that we can apply modern development practices. If we stop treating firmwares like a big black box that is deployed every month or even longer, but we treat it as an actual operating system upgrade, we can use faster development and testing procedures. We can do continuous build, we can do continuous testing, we can do a lot of things that are at the moment just not even considerable in the closed source firmware space. And the collaboration with the community is also great because we work with other people. We fix bugs for them, they find them fix bugs for us. So we all benefit from way more people's work. It's not just Facebook's engineers, but it's everybody else out there. Everybody moves faster. Code reuse is an obvious thing. I will give you some additional examples in a few moments. So LinuxBoot is modular and multi-platform, which means that, as I said, it can run on embedded devices in hostile environments like OpenCellular, but it can also run on high-end servers in data center in trusted networks. And it's literally the same blob of code, with the exception of the platform initialization, so whatever coreboot does with memory and silicon, everything else is exactly the same kernel image and RAMFS. And I will explain to you later how the system, LinuxBoot itself, knows how to behave depending on the machine it's running on. It's not just Facebook's hardware or OCP hardware, but you can also try this at home. There are several different boards. Anything that is supported by coreboot will basically work with LinuxBoot. For example, Chromebooks can definitely run LinuxBoot. We had a demo at the Open Source Firmware Conference where a Chromebook was running coreboot and LinuxBoot, and there was even an M-Player video running in the firmware itself. So the OS was not involved at all. And it's really interesting because anybody can buy one of these platforms in a retail store and run this firmware. So, as I said, not just servers. We run on switches, we run on embedded devices, we share the code. As I said, we get the benefits of continuous builds, continuous testing. The same testing infrastructure that we use for our software can be reused literally with small adjustments, minor modifications, can be used for the firmware testing itself, because now it's just software, right? And as I said, as I suggested in the previous slide, the runtime configuration is what gives the machine its personality. That says you are supposed to be working on OpenCellular in a hostile environment, so security requirements may be different on this platform versus what you would do if you're running in a data center server. So the boot configurations will basically decide how the machine behaves. And we also want that everybody is able to build these firmwares. And I didn't have time to put it in the slides because it's just very recent news. I'm going to publish, in the next few days, I'm going to publish instructions and configuration to rebuild the same images that Facebook builds on the OCP servers so that anybody can rebuild their own images. And of course, we will add testing and continuous build also on the public repositories. This is going to be published under github.com/LinuxBoot. So we have one single central place for all the LinuxBoot related stuff, even the company-specific ones. Security-wise, it's also adaptable to different threat models. As I said, OpenCellular switches and servers and Chromebooks have completely different use cases, but the same code can be adapted to different use cases. It's not just servers, but it's also not just firmware. As I said, another firmware engineer, I saw the chance with my team to use LinuxBoot components also outside of firmware space. Why not? In the end, it's a Linux kernel. It's a RAMFS written in Go. We have a lot of skills at Facebook with Linux and Go and other programming languages. So it was quite obvious to do the next step and use it for something completely different, like why don't we write a network installer that is based on LinuxBoot? It's a small Linux kernel plus the same RAMFS, plus, of course, a different behavior because it's not running in firmware. And we call it YARD. Names are hard. It stands for yet another RAM disk. And this network installer is just something that we download over the network. It's intentionally really small, so it can be downloaded easily via TFTP. But after it's downloaded via TFTP, you have the full LinuxBoot environment, just in memory rather than on the firmware. Another project that we created internally is called Prov Launcher. It was done by one of our interns that just finished a few weeks ago. It's very similar to network installer, but we pre-provision this network installer on the disks of the machines. This means that at the first provisioning, the machine will do the regular network booting with TFTP and all the risks that this carries. But all the subsequent installations will not need PXE booting anymore. So even if we don't have LinuxBoot on that machine, we can still benefit from LinuxBoot because it's on an image stored on the hard drive, and it's just a boot entry. So this boot entry will actually use the verified boot, HTTPS, proper DHCP clients, and so on. All right, so I mentioned system boot several times. Let's see what this is. So system boot, as I like to call it, it's a distribution. It's like Linux distribution that implements a bootloader. It's based on uroot, which is a RAMFS project written in Go, started at Google, and that we are helping to develop. It provides, system boot specifically provides different tools for different boot scenarios. So we are based on top of this RAMFS, but we add a bunch of tools and a bunch of functionalities, libraries, and so on that let us behave as a bootloader for multiple use cases. The goal is to basically to create one single image that can do can handle all the use cases for us. One single code base is way easier to handle than many different code bases that do similar things. So what's inside the package? This is just a laundry list. I'll go quickly through it, but then I have one slide for everyone. We have something that we call LinuxBoot VPD. It's a key value store that is stored on the flash chip. We also have a netboot command line program that, as the name says, will do net booting. We'll see more in the next slide. And local booting, very similar. It will do booting from any type of local storage. Commands are not the only thing that is implemented in system boot. We also have some libraries. Sorry, before the TPM tool. There is a booters interface, which is a framework and a specification that gives you a way to define your own booter and your own boot policy. But we also have high-level TPM libraries and tools. So if you want to deal with a TPM and you don't want even to know that it's a TPM 1.2 or 2.0, you can use the TPM tool library and command line to work transparently with whatever TPM version. Since this is written in Go, of course, it doesn't run just on LinuxBoot, but it can also run on your target Linux machine. And last but not least, the uinit. It's a name that uroot requires to be the first program that is run when you boot uroot RAMFS. This basically wraps everything around and decides what to boot next. So let's see how this fit together. The VPD library, as I said, is a key value store, and it's based on an existing project. VPD stands for Vital Product Data. Was created by IBM, and it's used on Chromebooks by Google to store runtime and machine information on the flash chip. And from how we use it, you can think of it in a similar way to the UEFI variables. We use it to store persistently information about boot configurations, but it's generic enough that you can use it for whatever you want. It can be extended, of course, but if you don't like VPD for some reason because you want to use NVRAM instead of the flash, of course you can swap the library out, and system boot will keep working with whatever library you write for your backend storage. Let's see an example. How does this work if I want to boot from the network first, and then if it fails, I want to boot from disk? Well, boot 000 is a familiar naming if you're used to UEFI boot manager. We try to reuse the same name so people know what this means, but the content is different. We decided not to go with machine with a binary format. We decided to use something that is easy to understand for both machines and humans, and is still compact enough to fit in a small amount of space. So we use JSON, and this JSON is very simple. It's a As you can see, there is a common thing that is type. Type is the only mandatory thing that says, this is how I want to netboot. My booting method is network on the example on the left, or local booting, as you see in the example on the right. It's also quite easy to understand. Well, you see, method DHCPv6. OK, it's pretty obvious that the machine will try to boot via DHCPv6. And the MAC address, I used a fake MAC address, but this means that it will try to do DHCPv6 on the interface that has that MAC address. If this fails, for example, because the MAC address is wrong or the DHCPv6 server is not responding, whatever the reason is, it will skip to the next entry, which will be boot 0001 and 2 and 3 and so on. And the second entry, again, it's very easy. It's very simple to understand. It will call the local booting method, and it will use it will call the local boot booter, and we'll use the path method in the specific case, where we specify the GUID of the partition we want to boot from, the path of the kernel that we want to kexec, and optionally you can specify an additional init_ramfs and the kernel command line, and potentially other information. Path booting is not the only one. Local boot is flexible enough that it can boot from in other ways, like from grub configurations, but we'll see this in the next slides. As I said, netboot is a program. It's literally a CLI program that you can run, and that will download a boot program via the network. So it uses DHCPv6 because we use IPv6 in our infra, but it can also use DHCP4, or if you want to skip DHCP entirely because you don't trust it, because it's unencrypted, it's not authenticated, you just don't like DHCP, you can also use Slack, which, again, it's not encrypted, but it's a much smaller domain of risk. Once the network configuration is acquired, the boot program will be downloaded via HTTP or HTTPS, which means you have to handle certificates, of course, but you also have security. And eventually, the program will be executed via kexec. Local boot is the other program. This is slightly more complex because it has two different boot modes. One is grub mode, and the other one is path mode. All of this is, of course, open source and publicly available on GitHub. The grub mode will try to will look for all the attached storage devices, which means anything that your Linux kernel is configured to see. It will try to mount all the partitions. It will look for all the available and valid grub configurations in the known grub locations, like /boot, /grub CFG, grub2 CFG, and so on. And if it finds valid configurations, it will try to boot them. You can decide whether you want to boot only the first one and fail if it doesn't work, if you want to try to boot all of them, if you want to look for a specific partition which contains a grub configuration, and so on. This gives you a lot of flexibility. Alternatively, if you know exactly what you want to boot, you can just specify the GUID and the kernel path, and if it's not present, it will just fail and go to the next boot method. Netboot and local boot are good, but you can do more. You can implement your own booter. For this, we created a booters interface, which is a very simple way to define how you want to boot. Basically, what it needs is just a method, a structure that contains a JSON configuration. This structure will have a method that will give you the type name, for example, local boot or netboot or whatever verified boot you want to do. And you will have to implement a boot method which contains your custom logic. Register the booter in the list of available booters, and system boot will automatically pick it up. An example that should be visible on the slide, I have highlighted in bold the relevant parts. This is the once you define the structure of the JSON that contains your JSON configuration, you can just implement the boot method, which, as you can see, just calls the netboot program -d for debug mode, user cross LinuxBoot to identify as a LinuxBoot machine. That's what we use internally. And then just run the command. If this fails, it will just skip to the next. And type name is as simple as returning a string that says netboot. Implementing your own booter would be as complex as this, at least for simple booters. Then you can implement your own logic, import external libraries, and so on. Anything that Go lets you do. TPM tool, as I mentioned, is a high-level interface for TPM handling. It can handle TPM 1.2 and 2.0. It was developed by Philippe Depenvise from 9 Elements and contributed to System Boot. This is not just a library, but it's also CLI that you can run on your Linux machine, and you can find more information about it on tpmtool.org. So let's see a demo. We have a couple of minutes. The static image was in case the demo was not working. All right, I hope it's visible enough. Okay, so this is an OpenBNC server for a Wedge 100S machine. And here I'm just sending a reset command to electrically power off and on the machine and connect to the serial console of this machine. The machine receives the reset signal, and then it will try to boot from the flash where there is a core boot image, which contains our LinuxBoot payload. So once the machine turns on, you will start seeing core boot messages. There it is. This is core boot. At some point, you will start seeing not any more core boot, but Linux messages. This is basically what you would see from a Linux kernel. We're still in the firmware. And I'm going to post the video here. So here you can see, after Linux has booted, there are messages from the RAMFS uroot, which, with its customization that we call System Boot, will try to actually boot the machine. It says, press Ctrl-C within 5 seconds if you want to stop it, and drop into shell. That's what I did in the video. And here you can see that it will try to boot. I Ctrl-C even after because it's a regular command. So once I Ctrl-C, it drops into a shell. And you can run basic Linux command like ls-shell. Here you see the list of files. This, again, is in firmware. You can run IPA or any other command to see the network configuration. And then I start local boot, the command that I mentioned in my previous slides. And this will look for the disk, kernel configurations, and boot everything. And that's as simple as that. As you've seen, there is a Linux shell, so you can literally run whatever command can run on a Linux machine. You can use TCP dump, you can use wget, curl, whatever, literally whatever you want. And that should be all. I'll hand this back, sorry, I made a mess, back to David.
All right, thank you very much, Andrea. So that was a tour of how we are utilizing Linux and, in our case, uroot and System Boot. We're using the same code. This is very important. We're using the same code that runs on our infrastructure in order to boot our infrastructure. And that's a big efficiency gain for us that was just demonstrated. So in conclusion, with LinuxBoot and open system firmware in general, you are in control of the firmware. For us, this eases integration and enables us to port and unify features across a big variety of platforms. It gives us transparency of security mechanisms and policy, enables us to use and create consistent tools, documentation, and processes, and enables us to test more continuously and thoroughly and be proactive instead of reactive when it comes to debugging. We're simplifying our stack and adding more capabilities. And that's not to say that Linux is necessarily simple. It just means that we're taking something that we already run anyway and then using it in a different context so that we're not duplicating a lot of code. We're doing for firmware what Linux has done for the OS. This is a natural, we are amplifying our firmware development capabilities by turning firmware engineers, Linux engineers into firmware engineers. Thank you.
Questions?
Yeah, let's do a couple quick questions. We know we're standing between y'all and lunch, so we'll try to be quick. Can you press the button on the microphone? Thank you.
I'm from Yandex company, and we have
many thousands of servers, and all the pines that you described, we very well know all of this. But there is a very negative side on the development. When you plan to develop new motherboard, you have to do this instead of BIOS or UEFI or BMC. You have to do this customization of this firmware for certain hardware. So how you deal with it? I mean, it's quite complicated process, especially for engineers who are not so deep involved in hardware design. Because now vendor, Quanta or Vivin or Gigabyte or somewhere do all this job. But in case if you do own firmware, how you deal with hardware?
Right.
Hardware related things.
Yeah. So yeah, typically when you have a new motherboard, the silicon vendor and maybe the ODM will work together to create a bring-up BIOS. So I guess the question there is, what's the value of doing something beyond what comes with the board to bring it up? And for us, this means, well, typically, in our experience, the initial firmware that runs on the system, typically it's something that, to begin with, it's usually hastily ported and often has a whole lot of bugs that need to be worked out anyway. So for us, we do work with the bring-up BIOS, of course, and we're going to continue doing so. But then sometime during during the development process, the production phases, EVT, DVT, PVT, et cetera, we'll remove the OS loader part and then replace that with LinuxBoot. And of course, we'll continue developing the full solution around that. So there is actually a lot of effort involved in this. It's certainly not something that comes for free. But in our opinion, we think that trying to make Linux the most responsible piece of software running on that platform is the most important part for us. Because again, we use Linux a lot as our runtime. So no matter which firmware you're using, whether it's Core Boot or LinuxBoot or OpenEDK2, in our case, Linux has to work very well, because that's what the machine is going to be running 99.99999% of the time. So in our opinion, even if we have to go back after the machine is already booted with its bring-up BIOS, if we go back and replace a big chunk of that with Linux, that's still reassuring for us, because we know that the Linux kernel that we're putting on there has been very, very thoroughly developed, and it has a lot of engineers looking at it who are continuing to debug it as time goes on. We want to continue to be proactive in developing and debugging the firmware. We don't just want it to ship from the factory and then pretend like we can forget about it, because that's never worked out for us. So I hope that helps clarify. Yeah, it is definitely a continuing investment. All right, great. So with that, let's go have lunch.